So continuing with the proof of the main theorem, which gives us a bound on the quality of packed learning as applied to Boolean functions, we will now move to step 2 and continue with the proof. But before we do that, I'll introduce 2 additional definitions that would be useful for us to move forward. Just to recap a well-known definition that we are going to use in building up those 2 definitions, I want to revisit the concept of the inner product of a pair of Boolean functions. So given functions f and g, as you can see on the screen, the inner product is simply the normalized, that is divided by 2 to the n, sum of fx times gx, where x takes on values from the set -1 and +1. And since we always describe n-dimensional functions, this would be n vectors or n element or n tuple inputs. So another way of, since we're dividing by 2 to the n, which is our version of this inner product, this is absolutely equivalent to this definition of the inner product, which is the expectation of fx times gx, where you're drawing x using our notation uniformly from the set of all possible n input vectors. In other words, it's important to remember that we have a uniform distribution from which we are picking the inputs. So these are the same definition. So they're essentially equivalent. So using that as a basis, what we want to now define is the concept of an L2 norm, which is a way of measuring how far functions are apart, and a very simple function called a sine function. So first we'll define the L2 norm. So if you consider Boolean functions f and g as before, let us just, for simplicity on the slides, write down f minus g to actually mean fx minus gx for the same input x. So we'll just write symbolically f minus g and not be bothered with writing the parentheses and the symbol x. Okay? So now, using inner product that we just revisited, the L2 norm is written using this syntax, is simply the inner product of f with itself. Okay? That's the L2 norm of function f. Now if you consider different functions f and g, not f by itself, then the difference between them, you can write it this way, which is measured under the L2 norm setup, which is the distance between them in this sense, is basically f minus g inner product with itself. So it's very similar to the L2 norm of f with itself, except now, given 2 functions f, g, you look at the difference, take the difference between them, and take the inner product of that. So that's simply the definition. And we know, going back several videos perhaps, I had flagged a particular formula using a double asterisk. You could easily write the inner product when we discussed it there, not necessarily as a product of the function values directly, but instead replacing them by their Fourier expansions. So since we know this well now, replace every function by its Fourier expansion. You could also similarly equivalently rewrite the function, and therefore, without going into details here, one could think of the L2 norm as being represented as the Fourier coefficients instead of fx values. Just a side comment, because what we'll do, we'll use this form using the Fourier expansion, which is the expansion that I show here briefly, which is the double-starred relationship, as our basis for taking the L2 norm or computing it, not directly on fx. The second concept we want to introduce is the sine function, and the sine function is practically as trivial as you can get. What it says is, given a function fx, sine of fx is 1 if fx is greater than or equal to 0, is minus 1 if fx is less than 0. So it maps it from positive or 0 values into a positive value and negative values into a negative value, but maps them into just 1 and minus 1 instead of having a whole range of possible values. So just remember these two definitions, and then we are ready to dive into our main proof again. And we'll use those, hence the background. So now we have a proposition, which is the second proposition that I said would be used by us, if you remember the roadmap for the proof. And building on this and the first proposition, we'll actually build the entire proof. So this proposition says that you're given Boolean functions f and g, where f is our usual type of function, which maps minus 1, 1 to the raised to the n vectors built from those, as always to minus 1 and 1. But g maps the same types of vectors into the reals, a fully general Boolean function. Okay? Then let us also suppose that f minus g under the distance metric through the L2 norm is less than equal to epsilon. I just want to make a side comment we'll come back to later. We are slightly duplicating or using the symbol epsilon to mean different things. In the main theorem, we had a meaning for epsilon. For this proposition, the value of epsilon is not the same. It just means a small quantity. So bear with us, for simplicity, we didn't want to have lots and lots of symbols. So we're reusing that symbol locally just during this proposition to mean epsilon in a different sense than epsilon in the general theorem. I'll repeat this again when we switch back to the old mode. But continuing with the statement, given that this bound is satisfied, and this is a elegant and simple way of sidestepping an important fact that we need to prove, sidestepping in the following sense. Now consider our hypothesis function h, which maps these n vectors back into minus 1 and plus 1. So it's like f, but it's defined to be simply the sign of g. So g is a general function. I give you a bound between f and g, but I really want a bound between f and h. So I said by sidestepping, what I meant was, instead of going through a complicated way of proving that f and h are related in a nice way, we will show and sidestep some of the difficulty by showing f and g are related in a nice way, and use that to eventually conclude that f and h are in a nice way, related in a nice way. So this is the premise. This is what we'll conclude. Okay? So to summarize that fact, because it's an important, useful technique used more generally by people who work in this field, g is an intermediate function that we construct, and our goal is to construct h, and we construct h from g by this sign transformation, and then we say if g behaves well with respect to f, then we know that h will behave well with respect to f through the sign function. So in order to prove this, let us consider the case that fx, okay, is not equal to sine gx, which is the interesting case. So if fx is not equal to sine gx, because if fx is equal to sine gx, then we're doing fine, right? So it's an obvious fact that since fx and sine gx takes on specific values, that the absolute value of fx minus gx squared is greater than or equal to 1. Because square of any quantity, and the value is at least, if they're different, they're off at least by 1, right? So therefore we have the distance function between f and h, okay? What is the distance function as we defined it? It's the probability that fx is not equal to hx. That's what we defined it to be back some minutes ago. So that's the same as the expected value drawn uniformly as before of the indicator function of fx not equal to sine gx. Because the indicator function, if you remember, is a function that takes on a value of 1 when some property holds and a 0 when it doesn't. So the indicator function is 1 when this assertion is true. Then that means we are going to essentially take this statement and replace it by this statement. And this is the replacement works because the expectation of the indicator random variable, that's this one, is equal to the probability of x equal to naught sine gx, that is this one, and hx equal to sine gx. So basically, this is a definition. This indicator's probability, I am saying, follows from this statement here. And so given these two facts, we basically can conclude that the quantity distance fh equal to expectation of the indicator variable of fx not equal to sine gx. So basically go through two steps. Okay. Now we do one more additional transformation. We say that this expression is less than equal to the expectation of fx minus gx absolute value, the whole squared. And that's simply because this value is greater than or equal to 1 whenever the indicator variable is 1. So since this value, fx minus gx the whole squared, dominates the indicator function value, since this is bigger and it's otherwise the expression is the same, this at this point this equality becomes an inequality. So that's simply all we did there. Okay. Now this expression, using the L2 norm definition but instead using the Fourier coefficients idea, a little bit of algebra will show that it's exactly the L2 norm. So this quantity is the L2 norm, and by hypothesis we assumed that in the hypothesis of this proposition we assumed that this L2 norm of f with g is bound by epsilon. But with that hypothesis, I can therefore say that this is less than or equal to epsilon, and immediately gives us the relationship between f and h, which is what we are looking for. So we went from f and h through g and got this bound epsilon to propagate from a bound on the L2 norm of the difference between f and g to apply to the distance between f and h. So that gives us the proposition, and now we will be using this to build up on the full proof. So using proposition 1 and proposition 2, our goal is to prove this main theorem. Since it's been some time since we looked at it, I'll try to repeat the statement of the main theorem we are trying to prove. So let's suppose that we had an algorithm that's trying to learn. We called it A, and it has magically access to randomly chosen examples as inputs to it. Okay, so it has the input and the f value provided by some mechanism, and additionally A can, through an oracle, identify a collection of sets which we said were script f, and these are subsets on which f's Fourier spectrum is epsilon by 2 concentrated. This is just repeating the theorem we set out to prove. Then using additional time that's polynomial in the size of f, n and 1 over epsilon, algorithm A can with high probability output a hypothesis h that is epsilon close to f. This is what we set out to prove. And our definition, just to remind you of, is exactly what we had in proposition 2. Distance fh is the distance function, which is the quality of how well we have learned. We would like to learn f, we learned h, and distance was simply fx not equal to hx, the probability of that happening defined over all the inputs. So continuing and trying to prove this theorem now, using propositions 1 and 2, which we need to remember, of course, wanted to make a side comment about something we are about to embark upon, and that is, in many of these combinatorial type questions of the sort we are dealing with, where you do combinatorial analysis, turns out sometimes knowing particular values makes the analysis very tractable and feasible. But the way you come up with this is largely based on experience. So an example of this is something I'm about to show you, has to do with how we come up with two terms. There is no systematic algorithm or technique I can give you for automatically coming up with these terms in general. Just so happens that based on the experience of the people who worked on this, these particular terms work well in practice and in the analysis of this theorem. So what we are about to show is that for each set S that belongs to this desired family described by script F, as stated in the theorem a second ago, algorithm A can, using proposition 1, if you remember the statement of the proposition, get an estimate of f hat S for each of those elements, which represent f tilde S as an approximation. Again, as a digression, I want to make two comments. One, we are approximating function f through our learning scheme. But second, each of the f hats that we are using to build up are in turn being approximated, if you remember, by f tilde. And we are talking about the second type of approximation. So what we want is f hat minus f tilde, the difference, to be less than equal to the expression you see there, which I can read out in a second. But here we are switching gears and coming back to using epsilon in the same sense as the main theorem. So now we are back to the old epsilon. We have left the form of epsilon, which had a different meaning, which we were temporarily using in proposition 2, but they're related. So what we're saying is f hat S minus f tilde is less than equal to square root of epsilon divided by 2 times square root of the size of this set F. And this entire right-hand side of this inequality, that's this expression here, corresponds to epsilon from proposition 1, basically. So the proposition terminology switch is we are back to the old use of epsilon, is what I'm trying to say here. So epsilon as used in the main theorem and in the proof here are now the same and different from the symbol epsilon used in proposition 2. So that's the second part of the clarification. So in case you start worrying about matching epsilons, they're different. Okay? And in particular, the epsilon that we just used in proposition 2 is essentially this expression. Okay? So the second part of what we are about to also assert is we want this assertion to hold with a probability that is at least 1 minus 1 divided by 10 times the size of f. The second element, we are pulling the rabbit out of our hat. So if you give me these two, which we'll later on see can be done, then we have the theorem. Okay? So these are just chosen to simplify our computation. So one step that is useful for us as we move forward to the proof is something called a union bound, a basic fact and probability. So if you have a set of events, A1, set of A2 through AN, then the probability of A1 union A2 all the way through AN is less than equal to the probability of A1 plus A2 and so on plus AN separately. And the reason is there could be overlapping between the sets, intersections, and those become duplicate counts and then hence are subtracted. Okay, so in our design, for each S belong to F, we have the probability of the estimate satisfying or being correct, which is f hat S minus f tilde S, is less than equal to square root of epsilon divided by 2 times square root of f, and that probability is at least 1 minus 1 over 10f. So an application of the union bound to these sets in F will give us ultimately the fact that the quality, this guarantee, is true at least with probability 9/10. So that we'll simply use the union bound on the members of the set script F. So that's the reason I introduced the union bound. So now with these two facts, let us consider the following step. So our learning algorithm forms the function g, which is the intermediate function to hop to h from f, or the other way around. It forms the function g, which is the sum over these sets in the family script f, f tilde s times x to the s. That's the function we are after. And h is simply sine of g. So our algorithm now does that. So it builds, given from proposition 1, the fact that we can build the f tildes, it builds the actual function g using the Fourier expansion. Okay? So given g, we have difference between f and g under the L2 norm is simply the sum of the set, which is now using the Fourier expansion formula for the L2 norm instead of the direct formula. I mentioned to you there are two ways of representing the L2 norm, either as fx gx, which is the inner product, or its equivalent Fourier spectrum representation. This is simply the Fourier spectrum representation, and I refer to this particular form which we refer to using a double star. Using that form, f minus g can be written that way. Okay? So this has two terms, the first term in the sum and the second term in the sum. Okay. So now the first term in the sum, we do know from the magic element we pulled out of our hat that we wanted that element to be bounded by a certain quantity, which is this quantity. So the first term is automatically bounded by that quantity, so we just replace that over there. That's by design, that's our bound. And from the union bound, we know this is true with the desired probability as well. That was just discussed on the previous slide. The second term, that this part is epsilon by 2, is a direct application of what it means to be epsilon concentrated. We discussed this in the previous segment. So just substituting for those two terms and simplifying, we get this to be epsilon by 4 plus epsilon by 2, which is less than epsilon, what we want. So that was just pure algebra there. Okay? So based on this and proposition 2, which helped us link f and g, we now know distance fh is less than or equal to epsilon, which concludes the proof of the theorem. So what have we learned so far? We have learned that we could effectively learn with some conditions or premises that ought to be true. So one of the premises is that we knew this set script f, or we know a good way of finding it. Okay? Is there an efficient way of learning or finding the set f, I should say? There is a well-known algorithm. If you're interested, section 3.5 of our book by Professor Ryan O'Donnell, which I've referred to in the past, has an explanation of how you do this. We just refer to it, so to us it will remain an oracle in the course. So this is called the Goldreich-Levin algorithm. It in fact shows a polynomial time algorithm for finding f such that a Boolean function f is epsilon concentrated. So we'll use that as a subroutine, a black box, whatever you want to call it, or oracle, but it exists. So using that, one of the conditions of our theorem is no longer necessary, namely, we said if we can find such a set script f, now we know that we can using Goldreich-Levin, correct? So what's the statement of the theorem? Just to remind ourselves again, if you have an algorithm A that has access to randomly chosen values of the function f we are trying to learn, as well as its function value, then the oracle which will give us the set f is Goldreich-Levin. So that oracle now goes away. So now we have an algorithm which will not make this a condition anymore, but the rest of the theorem therefore is now true because set f is epsilon by 2 concentrated. then using polynomial time in size of f n and 1 over epsilon, algorithm A can with high probability output a hypothesis h that is epsilon close to f. Okay? So now the part that I haven't reasoned in the past few minutes has to do with the time this takes, namely the computation running time. So basically what we want to do is to argue that it requires time that's polynomial in the size of f, n and 1 over epsilon. That's what we are trying to show. From proposition 1, each step that we use to build f tilde s takes polynomial n square, because of our construction, square root of f divided by square root of epsilon times log of the size of f time. Okay? And this we expect will be an exercise in the following sense, that if you look at proposition 1 carefully and actually look at the form that we have here, it's a simple substitution. So since we have, this is each step to build an f hat s. Now we have how many such steps? That's the size of script f. So then we get basically from the previous term a simple extension that the entire computation is polynomial in the size of f, n and 1 over epsilon. And that basically also tells us that the running time of the algorithm is within the bounds we want.